Okay, we begin Unit 4 with 3.9. We're talking about what are something called differentials, okay? When we use differentials, we are basically making an approximation, and it's important to point out what an approximation is. Approximations are useful when you can't find exact values, but in our case, we're going to do approximations for things that we could find the exact value for, but we're going to do this just to practice, okay? So, so starting with linear approximation. So, when we do a linear approximation, we're basically saying that a certain function, so here I have a function drawn in black, we're going to assume that this function, f, can be approximated by a straight line for a certain portion, okay? So I have this line drawn in teal, okay? And this line is a good approximation of the function for a range of values. Let's say this range of x values, okay? Now, obviously, if I go way over here close to the origin, this line is no longer a good approximation because as we extend the line, it would be way down here, and our actual function is up here, okay? But in this region, okay, the y values of our function in black are similar to the y values of our line in teal, okay? And so that's what we use a linear approximation for, is if we couldn't find the exact value of our function, but we could draw a line that was similar, at least for a limited range of values, okay? Remember, we can always write the equation of a tangent line if we have a point, c, f of c, and a slope, which we've learned that derivatives mean slope, so the derivative at c would be the slope. So these are just ways to write that. So we can always write the equation of the tangent line. We would have to know what c is. Okay, c can't act like a variable. It's got to be a constant. And then y is going to be our linear function. And as we pick x values close to c, the y values we get out are going to be good approximations. Okay, to illustrate this, we'll do example 1 here. We're asked to find the tangent line approximation to this function, y plus sine x at the point 0, 1, okay? What we can do is take a table and compare what the actual function is doing and then what our tangent line approximation is doing at values close to c, which in this case our c is going to be 0. C is our x value that we're looking close to, okay? And then we'll compare about how good we're doing here. Okay, so first of all, let me point out that we don't need a tangent line approximation for this function because 1 plus sine x is an easy function to evaluate. We just plug in values and figure it out. But again, we're doing this to practice if there was a function we couldn't actually plug in. So say you had a function but you didn't know what the equation of it was, you'd have to use a technique like this. Okay, so first thing, let's find the derivative. What's the derivative of f of x? Cosine x. Okay, so that's the derivative. We also need a point, so we need f of 0. Oh, sorry, it's already given, right? Okay, f of 0 is 1, right? Okay, so we have a point, we have the slope, we have to find the slope at 0, which is 1. You got it. Okay, so now we have a point and a slope. We can write the equation of the tangent line. It's going to be y minus 1 equals 1 times x minus 0. Okay, rearranging to solve for y, we would end up with y equals x plus 1. Okay, so there is our line that is tangent. Okay, so if I draw this, this is what I'm going to end up with. okay? 1 plus sine x is going to have a minimum over here at negative pi over 2. It's going to be 1 at 0, and it's going to have a maximum up at positive pi over 2. So, oops. Something like this. Okay, so I've drawn it to emphasize this, but as you can see, in the region between negative pi over 4 and pi over 4, even though it's a curve, it looks a whole lot like a line, right? Okay, so your book has this on page 228 as well. It shows you a pretty clear picture, okay? So we can use this tangent line approximation. So our approximation is y equals x plus 1. Our original function is f of x equals 1 plus sine x. Okay?
That's all?
That's the first part. Okay, so now we want to see, is this a good approximation? Okay, and the only way to judge that is to look at a table of values. Okay, so I'm going to scroll down a little bit and make a table. So if we choose some x values that are close to 0, okay, choose some x values that are close to 0, negative 0.5, negative 0.1, negative 0.01, and then 0. Okay, we're going to check and see what is our original function at these points, and then what is our linear approximation. Okay, our linear approximation is our y equals 1 plus x, or 1x plus 1. Okay. All right, so I have these, the book gives us these. You could use your calculator as well to compare. But we see at negative 0.5, our original function is going to be 0.521, while our approximation is 0.5, okay? The difference between the two will just be 0.021, right? Not too bad. All right, at negative 0.1, it's 0.9002 for our original function, 0.9 for our approximation. That's even better, right? They're even closer. Okay, 0.9900002 and 0.99. Okay, even better. And then at 0, they're both exactly equal. Okay, they're both 1. So our approximation gets better and better as we get closer to 0. You could do this on the other side of 0 and see something similar. I'm going to leave it at that just to show you this proof of concept. Okay, any questions there? Okay. Okay, so from our tangent line approximation comes this idea of something called a differential. Okay. All right, as we see here, so we have the distance from the x value that we started with, whatever c is. We can look from side to side there. That is going to be called change in x. So the distance we travel from c. So in our previous example, c was 0. So we went to negative 0.01. Well, that's the change in x there would be 0.01, okay, the distance from our original c value. Well, that we can manipulate how much we change in the x. The y is going to be a result of whatever the function is, okay? So we can, if we plug in, right, the change in y is going to be the difference between the function evaluated at your original point, okay, so that would be here. So if, which in this diagram, technically we could call this c, okay, so our y value here would be f of c, okay, and then the distance between that y value and then the y value, the y value of your linear approximation here, which would be f of c. Well, I guess technically that one's not f. Okay. Here we go. Okay. Okay, so our green function here is f. All right, so f of c plus delta x. Okay, so this distance, okay, is what we call delta y. We're going to say that that distance could be approximately the same as the distance between f of c and the y value of your approximation. Okay, and that's what is going on up here. Okay, so here we have the difference in y values, and it's approximately equal to the distance away on the approximation. Well, to find the approximation value at that point, all we need is a slope and a change in x, right? Because it's a line, all right? So it's the slope times the change in x. So we can approximate that delta y as f prime of c times delta x. So whatever our change in x is times the slope of the approximation, that is our differential. Okay, so our, there we go. Okay, so our definition is if we have a differentiable function that has x in it, okay, our differential, okay, dx is any, our differential of x is dx, our differential of y is dy, and it can be calculated by finding the derivative at a point, multiplying by the delta x at a point, okay. Here is one example of the kind of problem we would be given. So our first one here, we're given the function, that's our original function. We want to find the differential, and again, the differential is the difference between our original function and its linear approximation. Okay, so how different it is. If we look back at our original example, okay, we're looking at the difference between 1 plus sine x and 1 plus x, because that was our original function. Okay, so here we're given the original function, y equals x squared, and then we're asked to find dy at the value of x equals 1, and we're given dx. Okay, and then we're going to compare it to delta y, which if we look back up here, delta y is going to be, if we actually check what is the actual function's value, that delta x away. Okay, so let's go ahead and solve. So first of all, let's find the differential, and we're using the definition from right up here. Okay, dy will be equal to the derivative at 1 times dx, which is given as 0.01. Okay, so what is the derivative? Okay, so if we plug in, the derivative of x squared is 2x, so if we plug in 2 times 1 times 0.01, what do we get?
0.02.
You got it. Okay, that is our differential. Okay, and again, this is based on our linear approximation. Okay, now if we want to actually find the difference in y values between the original function, we have to be able to evaluate the original function, and in this case we can. Okay, here we're just saying what is f of x plus delta x, okay, minus f of x. That's it. And in this case, so it would be f of 1 plus 0.01 minus f of 1. Okay, and if we plug this in, we know what f is, right? It's x squared. Okay, so it's 1.01 squared minus 1 squared.
Wait, what is like delta y is like the distance between the original function and the f of x between this distance?
Delta x only deals with the original function f. Our linear approximation, it's as if all we did, take a look at this picture here. okay? Delta y is here.
Yeah.
Okay, so what's the y value at C, and then what's the y value some distance away from C, okay? So it's just looking at this distance, okay? The differential is looking at the distance between the original function at C and then the linear approximation at some point later. Okay, so back to here. We've plugged in 1.01 squared minus 1 squared is going to just give us, oops, 0.0201. Okay, so now note the difference between dy and delta y. What can you say about the difference between those two values?
dy is like the distance between the
But-
f of x.
But what can you say about these numbers? Look at here. dy is here, delta y is here.
They are similar.
They're very, very close, right? So that tells us that the line that we've chosen is a good approximation, okay? So since dy and delta y are close, that tells us that the line that we've chosen, the tangent line that we're seeing, is a good approximation for this function around this point, okay? Okay, so now we're going to take this information and we're going to illustrate that a little bit more and actually show what would the linear approximation be close to this point. And so we'll find the equation for the tangent line close to our c value, close to x equals 1. Okay, so at x equals 1, what is y? 1. Okay, so we've got a point. What is the slope at x equals 1? 2. Okay, so now we can write the equation of the line at 1. It's going to be y minus 1 equals 2x minus 1. Okay, y equals 2x plus, minus 1. Okay, so there's the line. That's the equation of the line. Okay. If we call our linear approximation g of x, we can compare our original function at 1 is going to be equal to 1. Our approximation at 1 also equals 1. So at 1, they're the same. If we move a little bit away, f of 1.01, it's going to be 1.01 squared, which is 1.0201. Okay, our approximation at 1.01 is going to give us 1.02. So again, those two values are very close. It's a good approximation, close to 1. Now, if I plugged in x equals 10, would it still be a good approximation? No, not anymore, okay? But for values close to 1, this is a good linear approximation or a good tangent line approximation. Okay, this is where this actually becomes important to use, okay? And we've talked about this in science class. When you take a measurement, so say you measure the side of a cube and you need to find the volume of that cube. Well, any error in your measurement, right? Your initial measurement is just the side, okay? You're going to do a calculation to get the volume, all right? Right? Side times side times side. Well, every time you multiply, you magnify the error. That's why significant digits are so important, okay? Differentials, we can use those to talk about error propagation. Propagation has to do with something going from one place to the next. Okay, so error, it continues and actually gets magnified the more calculations you do with it. Okay, so what we do is we assume that our x value is what we measure. okay? And we know that all measurements have some error, okay? So we would say that our exact value, so our perfect value, would be x plus some little bit that we don't know how much it is because we can't ever be perfectly perfect, okay? Then that delta x is your error, okay? All right, so it's a differential. Your error is like a differential, okay? So when we use that to compute another value, it's like plugging it into a function, f, okay? And then the difference between the function, so your calculation at that perfect value, and the calculation at your actual value, so whatever it was you actually measured things to be, okay, that is going to be the error in your calculation, or what we call propagated error, okay? So error in your calculation, all right? All right, so here is an example, okay? If we have a ball bearing, which is a sphere, and we measure the radius to be 0.7 inch, 7/10 of an inch, okay? And we know that it is correct to within 0.01 inches, okay? We're going to estimate the propagated error, okay, for the volume, if we find the volume, okay? So if it's correct to within 0.01, all right, then that means that the error, okay, delta R, it's not, you could say it this way. You could say R equals 0.7 plus or minus 0.1. Okay, have you seen things written that way before? Okay, plus or minus 0.1, 0.7, okay. Another way to say that is if we get rid of the 0.7 and kind of ignore the fact that we know it's 0.7, is to say that the change in R is between 0.1 and negative 0.1. Okay, so that's what we're being told here. Okay, you would like to find the change in volume. Okay, again, we could do this the direct way and just plug in, well, what is 0.8 and what is 0.6 and find the volume. I know we could do that. Okay, we're going to make an approximation for the sake of learning this. So our approximation is going to be that the change in volume is about equal to the differential. Okay, and we have to go back to our definition of the differential. If in general our differential is dy, right, the definition is f prime of x dx. That's the definition of a differential. I wrote it up here at the top so you can refer back to it. In our case, we're talking about dv, okay? So our dv is going to be approximately equal to the derivative of the volume times dr, okay? Well, what's the volume of a sphere?
1/3 pi r cubed.
That's it. Okay, so dv is going to be the derivative of that part, so 4 pi r squared times dr. Okay, we're also going to make the approximation that delta r is equal to dr. Okay, so plugging in 4 pi, and then we know that the radius, we measured it to be 0.7 squared. And then dr is plus or minus 0.1. Okay. What we're going to get is the value that we're going to have to add or subtract to the volume in order to get a proper volume. Okay, the volume could be anywhere between these two values. It's not going to be 0.1. Why? Because
No, it's like 0.0.
there's a calculation involved, right?
Yeah,
The calculation magnifies the error, okay? So our final dv, our differential, is
but it is plus or minus 0.01.
0.06158. Okay, it's 0.7 squared times 4 pi times 0.1, plus or minus 0.1.
0.01.
No.
What?
Okay, we have to multiply by all of these. 4 pi times 0.7 squared times plus or minus 0.1.
Why 0.1?
0.1 is our dr, our delta r.
Yeah, this is like within 0.01. So, yeah.
That's for the radius, right? We're finding the differential for the volume.
Yes.
Okay, so when we find the differential for the volume, the error is going to be different because we're doing a calculation. Okay. Okay, so the
it's like the formula shows like is.
oh,
Like,
I see what you're saying. I'm sorry. That's not. I thought you were. I thought you were talking about this, but you weren't.
oh no.
Okay. All right. I apologize. You're right. Sorry, I wrote this wrong all the way up here. So this is supposed to be. No wonder that seemed so large. 0.01. Okay, so sorry. The dr should be 0.01, not 0.1. All right, and then our final answer here is still intact. Okay, so when we looked at the error in the radius, we had plus or minus 0.01. Now when we're looking at the error in the volume, we're going to get plus or minus 0.06. So it's more significant now in the volume than it was in the radius because we've done this calculation. Okay. All right. Now, consider here we have a ball that had a radius of 0.7 inch to begin with, okay? What if we had a ball that had a radius of 7 inches instead, right? The same amount of error. Is that going to be more or less significant? Will it matter that it's 0.01? It'll be less significant, right? That idea of how significant error is, we're going to call relative error, and we've learned it in science as percent error, okay? All right, so to do that, we're going to compare our differential for volume, so our error for volume, with the volume itself, okay? So dV, just like we wrote above, is 4 pi r squared dr, and we divide by the volume to get relative error. Okay, so the volume, again, is 4/3 pi r cubed. Okay, so we see we got cancel, 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 cancel. Okay, so we're left with 3 dr over r. Plugging in, we'll get 3 times plus or minus 0.01 divided by 0.7. So note, the bigger the radius is there, the smaller your relative error will be, okay? So if we calculate that, we'll get plus or minus 0.0429. And if we put that into a percent, it's going to be 4.29%. Okay, so less than 5% error is not bad.
So the relative error is the same with the percent error?
Just with removing the decimal places, yes.
Oh.
So in science, we looked at, we looked at something similar. So, okay. Okay, so when we calculate differentials in general, all we need to know is to go back to dy equals f prime of x times dx. But we also have some really handy formulas for differentials, so we can do problems quickly. Okay, This goes back to looking at the Leibniz notation. If you'll remember, we talked about that a little bit. The idea that dy dx is the derivative. If this were multiplication and division, it's as if you could multiply by dx on either side, which, sorry, this is a multiply, and this is a multiply, okay? Then you would be left with dy equals y prime times dx, which is correct. That's what our formula is. Technically, that's not really how it works, but, you know, if you understand it that way, that's fine to kind of think about it there. All right, so we have a couple of rules for differentials. The first one, the constant multiple rule. If you want to know the differential of cu, where c is a constant, it's going to be equal to c times du. If you want to find the differential of u plus or minus v, where u and v are both functions, you're going to end up with du plus or minus dv. If you're looking at the product of two functions, you have to use the product rule here. So you'll get u dv plus v du. And then same thing with a quotient. U over v give you v du minus u dv over v squared. All right, so a good way to think about these is to, when you're applying this to find differentials, take the derivative first, and then you just multiply it by the variable that you are, the opposite variable, okay? So y equals x squared. We're trying to find the differential dy. First step, what's y prime? 2x, right? We've already talked about that. So dy will just be 2x times dx, okay? Y equals 2 sine x. We're trying to find dy. What's y prime? 2 cosine x. So dy will be 2 cosine x dx. I'm going to jump down here below. For x cosine x, again, we're trying to find dy. Now it's a little bit more complicated. We're going to have to use the product rule, okay? So it's going to be negative x sine x plus cosine x. All right, and if we multiply all of that times dx, we'll get dy. Okay. And then the last one down here, again, trying to find dy, but first we need to find y prime, which will be negative 1 over x squared. So dy is negative 1 over x squared times dx, or negative dx over x squared. All right, so that part should be pretty straightforward, right? Finding the derivative multiplying dx. It's the understanding why you're doing that that gets a little tricky, and that's fine. It takes practice and big picture, little picture, going back and forth. Okay, so here is an example with a composite function. So function within a function. Finding the differential. It's the same thing that we've been doing. All right, first thing, take the derivative. So f prime of x. Okay, it's a composite function. That means we're going to have to take the derivative of the inside, so it'll be 3, times the derivative of the outside, which will be cosine 3x. All right, to find the differential, we just write dy equals f prime of x times dx. In this case, f prime of x is 3 cosine 3x. That's it. And straightforward, right? Again, we'll come to why we need these in the next section or two, okay? But for now, you just need to understand how to calculate a differential. All right, here's one that's slightly more complicated, but still straightforward because you know how to take derivatives. All right, find the derivative right? Okay, so the derivative of the outside times the derivative of the inside, okay, which we can write as, the 2's will cancel, we can write as x over the square root of x squared plus 1, okay? So dy is simply that, x over square root x squared plus 1 times dx. Okay, any questions there? Okay, we can also use differentials to approximate values. Looking back and basically rearranging what we've already written out. So basically f of x plus some delta x, so some distance away. So we would want to know what f of x is already and then just have a slight, in physics we call it a perturbation, so something that's slightly different, it changes it a little bit. So there's our error. It's going to be approximately equal to our original function plus our differential. Okay, which we already know what our differential is equal to, right? It's f prime of x times dx. Okay, by definition, that's what dy is, right? So if we have a function and we know like a base part of it, but we don't know the specific one, we can take a look and approximate. So here, our function is square root of x, all right? So if we want to find some slightly different thing, so we know what square root of 16 is, but if we want to find square root of 16.5, all right, we can rewrite using this approximation up here, f of x, which will be square root of x, plus the derivative times dx, okay? And in this case, x is 16, dx is 0.5. Okay, so all we would have to do is plug in, right? So square root of 16 plus 1 over 2 square root of 16 times 0.5. This to this. We used this logic up here, okay? The idea that this new y value can be approximated with the differential, and then the differential can be calculated there, okay? So if we plug that in, square root of 16, which is 4, plus 1 over 2 square root of 16, so 1 over 8 times 0.5, which is 1 over 2. So 1 over 8 times 1 over 2 is going to be about 1 over 16. Okay, if we calculate that in decimal form, we get 4.0625. Okay, so now the actual value, okay, f of 16.5, so the square root of 16.5, is actually equal to 4.0620. Okay, so our approximation is not absolutely perfect, but it's close enough.
How do you know like fx equal x to 1/2?
That we're given that. So we're dealing with a square root function. So f of x is square root of x.
How do you know that?
It's given in the problem. So we're approximating this function, square root of 16.5.
Serious?
Yeah.
You see that?
All right.